together. And oh, let's see, he came to U of R in summer 2019 and has been working on magnetohydrodynamics and thermal convection with application to liquid metal batteries since then. And he was a great fit for the scientific goals because he's quite an expert on magnetoconvection for a long time, just not with technological motivation before. He earned a PhD in, gee, John, remind me, it's planetary physics?
Yeah, the name of the degree is geophysics and space physics. It's a little convoluted.
And that was at UCLA with John Arno, thinking about planetary cores and fluid flows in planetary cores. And he also worked for 3 years as postdoc with Rudy Koonin in Eindhoven, building a really colossal thermal convection experiment that's produced some very impressive results. So maybe without further ado, I'll hand things over to John to tell us about the recent experimental work on convection and electrovortex flow and related phenomena in liquid metal batteries.
Thanks for the intro, Doug. Let me try to share my screen and let's see if this works the way it did when we tested it. You all see the presentation view?
Yes, I do.
Okay, great. Thanks, Doug, for the introduction, and thank you, Alberto and Norbert for the invitation and for hosting this seminar series. And I should also thank all the co-authors that are listed here for all their contributions that they've made and are yet to come as well, since we still have a lot of work to do. So I'll be talking to you about a new experiment designed and built at University of Rochester to investigate the fluid dynamics in liquid metal batteries. So, well, since this is a liquid metal battery seminar, I guess everyone's probably familiar with why we're interested in them, but I'll start with some context anyways. So one primary motivation for studying liquid metal batteries is to facilitate the implementation of renewable energy sources like wind and solar power. So renewables tend to be intermittent, which is best captured probably by this duck curve on the right side. Can you see my mouse, by the way?
Yes, you can.
Yeah, so this curve basically shows how the peak supply of renewable energy, mainly solar, is available during the day, but the peak demand is much later in the evening. Essentially, there's this time mismatch between when the power is supplied and when the demand is. And this can have a significant impact on how effective renewable energy is. So one solution that's been proposed for this is the idea of grid scale energy storage. Basically, you take energy from when there's the highest amount of supply, store it somewhere, and then redeploy it later on when it's needed. And there are a lot of technologies in development for energy storage, but among them, liquid metal batteries has potential to be particularly cost effective. So a liquid metal battery operates on the same principles as a regular battery, essentially. There's the cathode, anode, and electrolyte layer. The cathode and anode material would undergo a favorable reaction, but they're being separated by an electrolyte layer that only lets positive ions through. And so then electrons have to follow a different path through whatever load you want to put on the system. Only difference is all of the layers are liquid. And actually that sort of is the underlying factor that makes them so potentially cheap. So the advantages are here. There's the assembly process is simple. Materials are fairly cheap. You can just pour these layers on top of each other and they'll separate themselves because each layer is denser than the one above it. Potentially also has very long cycle life because If you damage a regular battery, if you damage any of these layers, then that damage sticks. If it's a liquid, of course, that just goes away. It's self-healing. Disadvantages include the fact that you need high operating temperatures because you have to keep all of these layers liquid. And also sensitivity to motion, of course. If you shake this thing around, then the layers might mix with each other and short out the battery. Something else that happens in a liquid metal battery is, of course, flow. And flow can be considered an advantage or a disadvantage depending on the situation. On the one hand, flow can provide mass transport and improve mixing. This is important because one thing that can happen in a battery is that you have stagnant regions and you have buildup of solid alloys in those regions. Those build up at the top of the cathode layer and end up eventually penetrating the electrolyte layer and creating contact between the positive and negative electrodes, which shorts out the battery. On the other hand, if the flow is too vigorous, you have potential to rupture this electrolyte layer anyways. And also, even without rupture, flow might not be enough to prevent alloys from forming because there can be stagnation regions in there, and these stagnant regions will still have buildup of alloys. So yeah, it's a complicated question. So where do these flows come from? Some sources include thermal gradients in the system because there will be a sort of differential heating depending on which layer you're looking at. There will definitely be compositional gradients as there's lighter and heavier material moving around during operation. And of course, there are electric currents and there are induced magnetic fields and Lorentz forces. These are just some examples that I took from Kelly and Weyer 2018. It's a great summary of the kinds of flows that occur, and these are just a few examples. So it's convection at the top, there's Marangoni flow here, and a metal pad roll instability. I think Garrett talked about that last, or in one of these seminars. And these are just a few possibilities again, and the interactions between these different kinds of flows are largely unknown. And that's sort of where our experiment comes in. The goal of our experiment is to study two of these forces that may interact with each other. So in particular, thermal gradients in combination with electromagnetic effects. So we study this by subjecting a single layer of liquid gallium to these forces. And you can think of this as simulating one layer in a liquid metal battery. The advantage of using gallium is that it's liquid at room temperature, but it has similar material properties to the liquid metal battery materials. And we use a tank of 10 centimeter diameter by 5 centimeter height, or aspect ratio of 2. But we can also change out this sidewall component and get tanks that are shorter or taller than that, since there's a lot of possible geometries for batteries as well. So let's talk about the forces first that we impose on this layer of gallium and what kinds of dynamics we'd expect to see from them. So first of all, we have thermal gradients. During operation, you'd expect that there's a current passing through the system, and joule heating will occur in it. Almost entirely probably in the electrolyte layer, where the resistivity is the highest. In the cathode, this creates a stabilizing gradient where there's lighter material over denser material. But this interacts with compositional effects, which I'll talk about later. In the anode, on the other hand, this creates an unstable gradient. During storage, there should be a transient state when the heat in the electrolyte layer is still dispersing out from through the anode and the cathode. But I think in general, there's always going to be thermal gradients anyways, because this entire system needs to be heated in a way that keeps it in a liquid state. So let's talk about this unstable gradient really quickly. So an unstable gradient is caused by an adverse temperature gradient, in this case, where the temperature is higher at the bottom and colder at the top. And this causes fluid motions in the form of convection. And the convection takes on a lot of different forms, and the form that it takes on is kind of dependent on the forcing parameter, the Rayleigh number, which is essentially the ratio between the buoyancy and the thermal and viscous diffusivities in the system. The important thing to remember here is that the Rayleigh number is proportional to delta T directly. If the Rayleigh number is above some critical value, then you get convection. Below that, then the heat is just transported conductively. In liquid metals, this value is about 6 times 10 to the 4. In addition, the form of the flow also depends on geometry, and this is important for liquid metal batteries, again, because a lot of different geometries are out there when it comes to development. We're not sure what kinds of shapes these batteries will eventually settle on. And yeah, so there are a lot of different possibilities for the kinds of flow that occur in here, even just with regards to convection. So I also want to touch on how thermal and compositional gradients interact with each other. During the charging process, lithium is removed from the top of the cathode, and so the remaining material is denser than its surrounding and sinks, and this leads to compositional convection. Here's a simulation of compositional convection from persists et al. 2019, just to visualize it. During discharge, though, light material is being added to the top of the cathode, and that creates a stratification and suppresses flow. Now, if you throw thermal gradients into the mix, now during the charge process, thermal and compositional gradients are opposing each other, while in discharge, the thermal and compositional gradients are both stabilizing, and they would probably act in concert to suppress flow. Let's talk about what happens when thermal and compositional gradients oppose each other. This is something that I was kind of wondering about. Something that can happen when the density of the fluid depends on both temperature and composition is double diffusive convection. And I was wondering if this could like feasibly happen in a battery. So during the charge process, again, temperature is stable, composition is unstable, and this is a configuration for a type of double diffusive convection called salt fingers, which is visualized here from a simulation by Cheng and Srinivasan. The control parameter for this is R rho, which depends on the ratio between the thermal and compositional gradients. And the condition for it to occur is when this R rho is between a value of 1 and the ratio of the thermal and compositional diffusivity is kappa T over kappa S. And optimal growth occurs when R rho is somewhere around 1. I plotted R rho for sort of battery setup, and you can see that it would require a thermal gradient that's at least about 10 times stronger than the compositional gradient. So that's probably not going to happen in a battery. In a liquid metal battery, the compositional gradient is much higher than the thermal gradient. So we're probably unlikely to see double diffusive convection. If we go back to this original picture, probably what's happening is that compositional convection is dominating in the cathode during the charge process. In fact, if you compare the Rayleigh numbers, I think this is also a claim from persists et al. The compositional Rayleigh number is about a factor of 10 to the 6th greater than the thermal Rayleigh number. So we impose thermal gradients in our experiment by using heat exchangers. Each heat exchanger is essentially a copper coil that's coupled to a copper plate. Copper is the material that we use in order to maximize heat transfer and try to make uniform temperatures across each boundary. Each of these heat exchangers is connected to a reservoir of hot or cold water, and we can switch them around in order to create a convective or destabilizing gradient, which is what's pictured here, or we can just attach the reservoirs differently and we can have a stabilizing gradient. There are a few experimental considerations that came in. So there's a couple of ways that heat exchangers, that the temperature on these surfaces can become non-uniform. In one case, they might be too sensitive to convective plumes. So this is determined by the Biot number. Essentially, if you have a hot or cold plume impacting the surface, you want to make sure that that surface still stays at the same temperature. And that's characterized by the Biot number. And I won't go into details about that, but you can, in the convection problem, you can simplify it into this form where the Nusselt number here is the non-dimensional heat flux. And you want this number to be somewhere below 0.1 or so. And so for the maximum Nusselt number that we would get in our experiment, I calculated the Biot number versus the plate thickness. You can see that we need a plate that's thinner than about 1 centimeter or so. On the other hand, the copper coils are spaced out. And this is because we have to fit some instruments through them, and just in general, there's going to be some spacing between these coils. And in order to make it so that the surface temperature is uniform, we want to make sure that the plate is thick enough that it's not sensitive to the coil geometry. And Ibrahim conducted some simulations to show that somewhere in this range of about 10 centimeters, you want to get higher than let's say like about 5 centimeters, 0.5 centimeters or so in order to get uniform temperature gradient there. So we kind of found a sweet spot. We settled on a plate thickness of about 1/4 inch or 0.6 centimeters in order to take both of these factors into account. So now I want to talk about the kind of electromagnetic flow that we study. So if you take a look at our mock-up of the liquid metal batteries again, you can see that there are diverging or converging current densities in both the charge and discharge process, since typically this anode thing is the negative electrode is thinner than the positive electrode. We can show with a fairly simple calculation that this necessarily leads to motion. If you have an incompressible fluid with an external force, and let's say this force has a non-zero curl, you can write Navier-Stokes equation like this. Now let's assume that this flow is going to be stagnant. Then it reduces to just the pressure term on the left side and the force on the right side. If you take the curl of this, you know that the left side goes to 0 and the right side doesn't go to 0, as we already claimed that the force is that the force has a non-zero curl. And so essentially this shows that if you have a system where the force has a non-zero curl, the flow can't be stagnant. There has to be some kind of motion that occurs. And in the case of liquid metal batteries, the kind of motion that occurs is electrovortex flow. If you have a diverging current density in an axisymmetric system, this produces a Lorentz force with non-zero curl, and the electric currents interact with their own magnetic fields in order to generate this flow. The strength of electrovortex flow depends on this EVF parameter, and it's proportional to the imposed current squared. And the velocity is in turn proportional to this S parameter raised to a factor of 1/2. And the shape that you'd expect it to take is this kind of strong descending jet in the middle underneath the negative electrode. The flow can also easily take on other forms though. So for example, if there's an external magnetic field or even something that perturbs the Earth's magnetic field in the vicinity of the electrodes, you can get an onset of something called a squirrel flow, where there's a azimuthal motion that quickly overtakes a lot of the dynamics in the system and makes this jet unstable. In our experiment, we impose electrovortex flow by having a wide positive electrode and a narrow negative electrode. So the negative electrode is a small copper rod that's isolated from the top plate by a plastic fitting, while the positive electrode is the entire bottom plate. And this is a simulation well, it's a theoretical result by Garrett Horstman showing what kind of current distribution you'd expect in a system with our geometry. Here's a clear diagram of the intended current paths through the experiment. So the power supply can supply between 0 and 90 amps. The top electrode is a plastic fitting with a copper rod inside, like I said, but there are several interchangeable electrodes. And the bottom electrode, it's technically, there's a rod coming in to the bottom that carries current into this plate. And for both of the positive and negative electrode rods. These are at least 0.5 meters long in order to avoid horizontal currents generating vertical magnetic fields that could interfere with the flow. So if we move on to diagnostics, we can see that, so for temperature measurements, we use thermocouple probes that are installed in the top and bottom boundaries. These allow us to measure the temperature roughly at the fluid layer, and they give us a good estimate of the Rayleigh number. For velocity measurements, we have a number of ports installed around the system, and these hold ultrasound probes. So velocity measurements are difficult in liquid metals because liquid metals are opaque, right? If you have a transparent fluid like water, then you can get 2D or 3D flow fields using PIV or other techniques like that. But in an opaque fluid, ultrasonic Doppler is the best option that we have for getting an idea of the flow patterns inside. So these probes only measure velocity along one line, and so we have to place them intelligently in a way that that sort of describes, it gives us the clearest picture of what the flow structures are. And this is just a diagram of where these probes are placed in our system. In order to describe how UDV probes work, it's probably easiest to just go with an example. So here's an example of time averaged UDV signals from several of the probes here. The color on the plot represents the probe number over here. They're color coded the same way. And so let's first take a slice in the YZ plane and look at that. Probes 1, 2, and 3 are plotted on the left side. And so this shows the velocities along each of these probes. Probe 1 has fairly low velocities, so let's assume that there's not much flow going on there then. Probe 3 has a strong positive velocity, especially in the middle, and so that indicates that there's a strong flow going away from the probe. On the other hand, probe 2 has a similarly strong flow going with negative velocities, and that means that the flow is going towards the probe. And the same sort of thing can be done for the vertical probes 8 and 9. So that indicates that there's a strong flow going away from 8 and a relatively weaker flow going towards 9. And you get this kind of picture that there's a single container scale circulation taking place in the system here. If we plot these values in a time-dependent way, we can, in a movie, we can see that that more or less reflects what's going on. Doug wrote this really nice program for visualizing UDV flows with respect to time. And yeah, it looks like there's perhaps like one container scale circulation as the dominant flow mode here. So we characterize the dynamical properties of the flow using the Reynolds number, and velocity measurements play into this because of the way that Reynolds number is defined. So the question though is how you estimate the Reynolds number in using UDV. So in flow field measurement methods like PIV or particle image velocimetry, you can sort of get a general idea fairly easily for what typical velocities are like. But in UDV, you only have one component of the velocity for each probe, and only measurements along these probe lines, of course, so a small portion of the volume. So estimating Reynolds involves some careful thinking. We could take the overall mean or RMS velocity by looking at this whole, the velocity over this whole thing, but this might be misleading because a lot of the flow could be out of the, could be not parallel to this probe. So perhaps only this peak region here is reflective of the actual velocity that's happening, where the velocity and the probe beam are lined up with each other. So that's another method of doing it that we thought of, where you just look at regions of the peak velocity, find a value of velocity that's within the vicinity of that, and then look at taking the mean of the velocities in this region, or the RMS of the velocities in this region, or the RMS of just when the velocities are hitting peak values in that region. These are just 3 other methods that we came up with here. And then apart from that, you also have to do this for every probe and then decide how you want to combine data from different probes. So maybe some probes are more representative of typical velocities while others are not, or you can just sort of average all of the values together. So that's what I've done first. I've averaged, I start out by averaging all of the UDV probes, and then I apply all 4 different methods for estimating the velocity here. And you can see that I've plotted the Reynolds number here versus the Rayleigh number, and they seem to fit these power law scalings, although some of these techniques do a better job than others. A general observation is that you can see that there's a large variation in the absolute values of the Reynolds number. But they do seem to lie along these power law scalings. A prediction from Grossman and Losa theory is that the Reynolds number and the Rayleigh number should scale as 0.5. And some of these methods do a pretty good job of fitting that scaling, while some of the others are maybe a little bit poorer than that. We've been talking about water convection so far, so let's move on to gallium convection. Gallium, we have the same setup of UDV probes. You can see though on the left side that gallium signals are a little bit messier in the UDV data. There's a larger region of noise in the front, and in general, you have a kind of noisier signal in the bulk as well. But maybe surprisingly, when you plot the Reynolds number versus the Rayleigh number, again, you still have a fairly large variation in the absolute values depending on what method you use, but they all agree quite well to the power law, and they all have very similar scaling exponents. For a liquid metal, Grossman and Losa theory predict that the Reynolds number should scale as Rayleigh to the 0.4, and it seems like they all line up with that pretty well. There's still quite a bit of work to do to figure out what the best way to estimate the Reynolds number is in terms of the absolute value, and that'll involve comparing with values in the literature and sort of looking at the flow itself and seeing where things are perhaps most representative of the actual velocity in the system, an actual typical velocity in the system. Let's take a look at probe 1 in detail now. If you look at the time average velocity signal, it looks like there's not much going on there. But actually, there's a strong flow, but it's time dependent. What I've plotted here on the right side is a Doppler where you have time plotted on the y-axis and distance from the probe, so the position plotted on the x-axis. And velocities are plotted in the color here. So what you can see is that throughout time, you get strong negative peaks in velocity and then strong positive peaks. These alternate with each other, and they have a certain signal to them, a certain periodicity. When you plot the FFT of this, you can see that that this peak exists here at around 0.054 times the free fall frequency. This periodic signal resembles something found in Vogt et al. Paper in 2018. They describe this as a jump rope vortex. So it's a large scale circulation where the vortex core, instead of being stationary, is kind of bent around in this kind of croissant shape, and it undergoes a periodic motion. And this periodic signal that you see here is the overturning of the vortex core. If we look at the signal on all of our other probes, we can see that this periodicity is still present. And in fact, even if we look at the temperature data, we can see that even though the probes are not in direct contact with the fluid layer, they're just sort of touching the copper plate. We've drilled in a little bit, so they're somewhat close to the fluid layer. But there is a really strong periodic signal there in the temperature data as well. And if you look at the temperature power spectrum, you can see that this has a very similar peak to the velocity power spectrum. Now, if we plot these primary peak frequencies versus the Rayleigh number, what I've done here is I've taken all of the UDV probes and all of the thermocouple probes and plotted them together. Well, actually, Jared did this. They seem to lie along a power law scaling versus the Rayleigh number. And this is also predicted by Vogt et al. Because the jump rope vortex frequency is predicted to be directly proportional to the Reynolds number. So the JRV frequency should follow the same power law scaling against the Rayleigh number that the Reynolds number does. And if we take all these average values and plot the thermocouple data and the UDV data separately, we can see that both of these frequencies are proportional to Rayleigh to the 0.38. Once again, in liquid metals, we expect it to be a factor of about 0.4, which is a fairly close agreement. So I think we've gotten a little far afield. How does this apply to liquid metal batteries? Well, I think that the interesting thing here is that the jumper vortex gives direct information about the state of convective turbulence in the system, but without any actual direct velocity measurements. All you need is a temperature probe in the vicinity. I say temperature probes here, you probably only need one to see it, in the vicinity of the fluid layer. And you have information depending on the scaling between F naught and Reynolds, or the prefactor for that scaling. You have direct information about the dynamical properties of the system that way. Another idea that I was wondering about, and I don't have any proof of this yet, I probably need to look at simulations to figure this out. I wonder if this kind of vortex core has less stagnation regions than a regular large-scale circulation. So in a regular large-scale circulation, the vortex core is stationary and fluid parcels are kind of trapped there inside that central region. But in the jumper vortex, this vortex core is orbiting around. So the question is whether it's taking the same parcel of fluid and just sort of rotating it around, or if it's always incorporating new fluid and spitting new fluid out as it goes through its orbit. If it's the latter case, then that might actually be very useful for liquid metal batteries where you're trying to avoid stagnant regions. So, of course, there's some open questions before going that far. We know that they occur in flat aspect ratio tanks. And so what range of aspect ratios do we get jumper vortices? How does the relationship between the jumper vortex frequency and Reynolds change with aspect ratio? I think we expect that the exponent, that the power law scaling remains the same, but there's probably a different prefactor defining the relationship between the frequency and the Reynolds number. And finally, what about different boundary conditions? In a liquid metal battery, you have at least one free surface for each of the layers, while in our system, we have all non-slip boundaries around it. So we would have to test it out with a free surface and see if we still get a jumper vortex. So let's move on to electrovortex flow results now. So these are created once again by imposing a current through a narrow top electrode and a wide bottom electrode. And if you look at where these probes are located, these results are a little bit more mysterious, but you bear with me because I think there's some interesting stuff happening here. So as expected, the flow is largely triggered near the top electrode, and so you have weaker flows as you go further down. Probe 2 has a weaker signal than probe 1, which is weaker than probe 3. It has the strongest signal here. The flow is concentrated near the electrode, which is what we expect since the majority of Lorentz forces are occurring right here at the edges of the top electrode. At first, we were wondering if this type of flow shape was caused by Joule heating and not electrovortex flow, but we calculated the temperature gradients and it definitely doesn't seem to be the case. So there is some kind of electrovortex flow going on, although the shape of it is perhaps different from expectations. Either way, though, let's take a look at what happens to electrovortex flow over a different range of currents. So when we have a low current, we see something like a stable jet, where the motion is mostly constant in time and also in space. It's roughly the same size, the same breadth, I guess, and over this whole period of taking data. And I'm only going to be talking about velocities in probes 3 and 4. These are the ones located at the top in radial positions, and so closest to where the flow is going on. On the other hand, when you have high currents, you get this kind of unstable jet where the flow varies widely, both in the strength both in the velocity and in the sort of horizontal extent of the flow. So what exactly is happening between these two cases? I'm not sure. There could be onset of swirl flow that's perturbing things here, and that could be caused by interfering magnetic fields, or maybe there's some perturbation of the momentum boundary layer caused by our experimental design. So as you can see, we have some probes installed in the top, and there's also an electrode installed up here. And something that's not pictured are that we have a couple of holes, very small ones, maybe 4 or 5 millimeters in diameter, that are meant for filling and draining the tank of gallium. So maybe those are perturbing the momentum boundary layer and leading to some kind of instability in the flow. I'm not really sure what the cause is here. Anyway, though, I want to focus on what happens near the transition. So if you're very close to the transition region, we get this strange periodic signal that shows up that seems to have multiple peaks. One idea that I had is that this is caused by stable stratification. So if you look at the temperatures here, I've actually imposed a light, stably stratified setup where the top temperature is slightly warmer than the bottom temperature. And the reason for this is that if you have any kind of destabilizing temperature gradient, convection is likely to dominate the system very quickly. So I've tried to do a stabilizing gradient in order to counteract that. But if you have a stably stratified layer, there's a possibility that perturbations can kick off internal waves. And the frequency for that should be the Brunt-Weisel frequency. I've estimated it over here by just taking the overall density gradient over the total height of the system. And that comes out to be around 0.11 hertz. It doesn't really line up with any of these peaks. Maybe it's kind of close to this light peak over here, but I'm not sure. It's just, one potential, one guess for where this periodic signal is coming from. I'd love to hear other people's ideas if you have them. Here, there's a stable case that's a little bit below the transition area, and you can see that it starts out with an initial periodicity. It still has that periodic signal, but it's suppressed, and eventually it dies out and turns into a regular stable case as we've seen before. And then if we look in the middle of the transition, there's a strong periodicity here, and we can see that there are multiple frequency peaks. One of them lines up kind of well with the Brunt-Weisel frequency, but once again, this is just an estimate of it, and there are any number of other possible sources for this kind of motion. In order to test this, I'll probably try to change temperature gradient by small amounts as well. And the other part that's difficult about this is that this isn't totally consistent behavior. We always see some kind of frequency peak, but I've just picked the one that has the strongest signal by far. There's some where it's a lot weaker and you can't exactly see where these peaks are located. So I think I should also address the sort of elephant in the room. If you look at electrovortex flow, the theoretical derivation of it should be some kind of axisymmetric flow, where you have a jet going downward in the middle and all other flows are going towards that jet, where probes 3 and 4 should be located. But that's not what we get. We get this negative peak here that indicates flows going strongly towards probe 4 in the middle. And for probe 3, we see this strong negative jet and also a positive flow going away from the probe right after that. And so there's something going on here with our electrovortex flow setup that I don't quite understand. There's one thing that we noted is that there seems to be a dependence on the position of the top lid. So once again, maybe there is some electromagnetic effect from materials on the top lid. We've tested this out by replacing everything that's conductive on the top lid with that's magnetic on the top lid with non-magnetic materials, but we still get kind of a similar result here. So maybe it's because of perturbation of the momentum boundary layers, like I was saying earlier, from holes or other divots or something in the top lid, or maybe the current is going in places that we don't expect. Either way, we're testing this out by rotating the top lid through a lot of different angles. If you look at the diagram below, you can see that there are 6 possible positions that we can rotate, or more than that. But we can rotate this top lid through several different positions and see how that changes the flow that we get during, when we apply current. And a future test that we can do is just to remove the top lid entirely. We can design a version of this that's hollow, and we can track flows directly by applying the electrode to a free surface. It will be a slightly different problem, and we won't be able to get some of the diagnostics or temperature control that we want. But either way, it's something that we can test out. So I'll leave you with that in conclusion. The viability of liquid metal batteries depends heavily on the flows that are occurring in them. And important flow forcings include thermal gradients and electrovortex flow. Their combined effects are not totally well understood, and that's the motivation for why we designed this experiment. We want to explore how these two flows, these two forces interact with each other. In convection cases, these are dominated by the jump rope vortex signal. It's the most prominent mode. And they might be relevant to liquid metal batteries for a variety of reasons that we still have to sort of suss out in detail. In electrovortex flow, we see stable and unstable jets, and we see strange periodic behaviors. And for future work, we have quite a few mysteries to solve. We have to figure out what's going on with the electrovortex flow asymmetry and why there's a dependence on the top plate orientation. We want to try out containers of different aspect ratios and a free surface setup. This free surface setup will be useful for both figuring out what's happening in electrovortex flow as well as trying to reproduce a jump rope vortex with a free surface. And then finally, the overall goal of the study is to find some dominant flow modes over a broad range of parameters. So I've shown you some specific cases. We want to see how everything ties together if you look at a lot of different flow forcings. Okay, thank you.
Great, just on time. Excellent. Thank you very much for the nice presentation. I think we have enough time for questions. If there were any from the audience, so please, if there are questions.
Yes, can I ask a stupid question? In the future work, as you said, you would like to study free surface setup. So what do you mean exactly in case of you want to study electrovortex flow, right? And so you want that the current flow through your through your liquid gallium. And so how do you manage with the free surface to inject the current and let it circulate? I mean, what do you really mean by free surface?
So
because you need a small let's say a small current collector and another one just to get the electrovortex flow to go around, right?
Yeah, indeed. So we will have the same setup at the bottom, right? This is the current collector on the bottom. On the top right now we have the top electrode is just held in by this little plastic fitting, but we can suspend it in a different way above the fluid and coming in contact with the gallium, if you imagine it. So the current still has to pass through this electrode, but it will be suspended by hopefully non-conducting materials. We'll be able to circulate a current through that way. This is similar to the setup that previous grad student Rakan.
All right. Okay. Thank you.
I hope that makes sense.
More questions? Jonathan, is the lateral wall isolated, thermally isolated, I mean?
Yes, so you can kind of see it briefly in this last slide. We actually have even more insulation that we put on other than this, but basically the entire system is all surrounded by insulation.
Okay. So, because I was thinking that probably convection from this lateral wall may induce these oscillations.
Yeah, that's certainly possible, but I think that our thermal control is fairly good, and we have temperature probes. Well, we could also put temperature probes along the sidewall, but the ones on the top and the bottom seem quite consistent with the temperatures that we put in through the chiller and thermal bath.
Thanks.
I have a question in chat from Michelle Rivero. I hope it's okay to respond to this out loud.
No, we don't have
Um,
questions in the chat.
So he asks, in our experiments, did we consider possible inclinations of the container? So, you know, if there's a small inclination that could break symmetry in the flow. And that might... So that is something that we should test out. I mean, our flow, we can orient it in a lot of different ways, and everything is leveled quite carefully, but it could be possible that a small change in the inclination would be something. I think that we have already sort of, the tank is just naturally inclined in different positions when we set it up. We do get consistent results when we have the top lid in any given orientation. So that might make it a little bit less likely. But yeah, that's also an idea.
So for most of the experiments were run for a temperature difference of less than 1 Celsius degree, or
I'm sorry?
the most of the experiments were run for the temperature difference of more than 1 Celsius degree. What was the temperature difference?
Yeah, so the temperature differences that I go through are anywhere between like 0.5 degrees Celsius. It's probably the smallest that we can do and have decent control of the temperature. And up to, in water, about 30 degrees, and in gallium, about, I think, 15 to 20 degrees. Gallium is much more conductive, and so it's hard to pass. It's hard to give it a really strong delta T.
From 0.5 to 20 for gallium. Right?
Yeah. So the figures that I showed, where I plot the Reynolds number versus Rayleigh, this is over a large range of.
Did you try to fix the temperature difference and to explore the different current values, and then try to fix a current value and then to try to explore different temperature difference value?
Yeah, so that's the idea. In fact, eventually the idea is to sort of get a whole phase space where you see all of the changes with a fixed temperature and different current, and fixed current and different temperature. Kind of a 2D diagram. Yes, Eduardo?
Yes.
Yes, well, thank you very much for your talk. I think that you have shown us very intriguing results, in the sense that the flow is very complex, and it's very difficult to reconstruct it with just probes that give you information along of the velocity along lines.
Yes,
but I was wondering whether we can try to look at the whole flow, obviously not using a liquid metal, but something like an electrolyte or something that allowed us to use PIV. Would it be possible to reproduce some kind of more or less the same or similar situations, even though the Prandtl number is very different between the two?
That's kind of an interesting question, because so I think that as far as Prandtl number goes, there's kind of a hard cutoff in behavior, right? If you have, Chandrasekhar predicts that if you have Prandtl above about like 0.36, you get one family of behaviors, and below 0.36, you have another family. And I'm not sure what materials, maybe Bitong has a better idea for these things, but I'm not sure what kinds of materials would have this property of being below Prandtl number 0.36, but also transparent. There could be some out there, and also electrically conducting. The only ones I know of, though, are liquid metals that are opaque. I think the problem is if you try to compare with higher Prandtl numbers, that you get very different behaviors, and it may be hard to do.
Yeah, I agree. But it seems to be very difficult to reconstruct the three-dimensional details by just using this these probes that give you very limited information.
Yeah, so there may be a possibility to do a better job as well. results that I show you on electrovortex flow at the end are only the horizontal probes. And the reason we did that is, the reason I've only shown those, that I removed the vertical probes since they were somewhat close to the electrode, the negative electrode, and I was worried that they'd be interfering with the flow. But I'm not sure if that's the case. I think, I hope you don't mind me asking you, Norbert, in your setup, you have UDV probes that are around like 2 millimeters or 2 centimeters or so away from the top electrode, right? And you're able to produce electrovortex flow without interference from them?
I think the probes, can you see me? We had the probes nearby, near to the electrode, and they were put in such a way. So basically they should not interfere with the current. But we were never happy with the measurements, and we already removed the complete experiment. It disappeared now.
You do have a stable jet in some experiments though, right?
It was never stable. It was always like that, oscillating, but we had 80 ampere because we simply did not try it with a smaller current. So it was really chaotic, unsteady.
I see, yeah. Yeah, so far for us, it doesn't matter what happens. If we have a high current, then above like maybe 15 or so amps, it's always unsteady.
I'll jump in response to Eduardo's question. The broader question about learning more about the three-dimensional structure of the flow. And well, another thing John's been working on, and this is not, it's not ready for us to present anything yet, but we've been trying to use physics-informed neural networks to do physically relevant sort of interpolation from the times and places where we actually have measurements to times and places where we don't. And he's got some nice results, at least for like 2D simulations. We're going to push on that and see if we can do anything with it. I don't know. Maybe John wants to say more.
I probably won't say too much more about it for now, but the idea is that we can kind of reconstruct the flow field from a small number of measurements and the equations of motion. And you know, of course, you have to be very careful with machine learning techniques because a lot of it is black box. So that's why we want to be careful about talking about the results. It seems fairly promising so far. Carolyn?
Yeah. So yes, I would like to ask a question about the gallium convection experiment. When you said that you were measuring a one roll structure with a jump rope vortex in the middle, so how can you be sure that you have only one roll? Because what is strange is that the orientation of the roll should be just you know, you can't really choose the orientation of the roll with respect to your probe, right? So
Yeah.
do you do something such that you're sure that you will be able to measure the main horizontal velocity in your with your probe? I mean, do you do something to stuck the roll in such that you can measure it?
So that's the interesting thing, is that we don't do that. And that's why I was worried that Reynolds numbers measurements wouldn't pan out, right? Because it could be that the probe just happened to be oriented the wrong way, and that the flow is not, you know, none of the interesting parts of the flow are in plane with the
probe. Yeah.
But we do have probes oriented in many different directions, and this also touches on another question. We also have non-radial transducers in there as well. And all of them detect this signal fairly well.
Uh-huh.
At the end of the day, it's interesting, I guess, that we get this signal no matter what the orientation of the probes are. So it could be, so sorry, sorry, with regards to the Reynolds number, that probably has some effect here. But for some reason, when you average through everything, it seems to average out the fact that the probes are not that the roll is not necessarily oriented with regards to the probes.
Mm-hmm.
And
So
that's
the
kind of mysterious to me.
yeah, and so this main roll is kind of stationary, but it's only the middle which is periodically rotating like a precession rope, right?
Yeah,
That's
and
what you
I
said.
think you see the signal. It's probably most clear here if you look at probe number 8. This one is oriented very close to the sidewall, and it has the weakest signature of the drum rope vortex. I believe that if you plotted an FFT of probe 8, you would still see a peak there, but it would be less strong than the others. But yeah, in the middle of the container, you have.
Yes, I see.
But towards the side, it's a bit.
All right, thank you.
There was another question in the chat that I want to
Yes,
address as soon as
I can't see any questions on the chat. Can you see it?
Yes. So Michelle asks, the UDV transducers are in direct contact with the gallium, and they might affect the flow. So yeah, that is one question. The UDV transducers are in direct contact with the gallium. Mechanically, I don't think that they should affect the flow. So I don't have a good diagram of this, but if you look at the if you look at the fitting that we use here, the back part of the fitting matches up perfectly with the back wall, with the inside wall of the tank, and the UDV probe fits perfectly inside of this fitting. And so there are perturbations on the scale of like maybe a millimeter, half a millimeter or so in that part, but they generally create a fairly smooth wall. If they're creating some kind of, if they're distorting the flow because of electromagnetic effects, that's possible. I'm not really sure about that. It could be that currents are being diverted a little bit by those. I think that it shouldn't matter too much if they are far away from the electrodes. But then again, I don't know exactly how far away is too far away, or is not far away enough. And also you mentioned that that it didn't show measurements on the non-radial transducers. There was no particular reason for that. If you want, there's one here, probe 5, that's oriented in a chord position. Probe 6 and 7 are also in a chord position. I could also go into more detail about the strength of the non-radial flow here in electrovortex flow results. We do see some kind of weak swirl signal. It's usually, I think in all the cases that I show here, it's on the order of about 0.5 millimeters per second. Significantly weaker than the non-radial flows, than the radial flows, but still present.
Thank you. Probes number 8 and 9, do they penetrate the upper Cooper plate or not?
They do.
Okay, so this will not affect the temperature distribution on the top plate?
I don't know. I don't think it does. The top plate should not be experiencing current is the idea of this design. Because the upper electrode is isolated from the rest of the top plate. But if they are magnetic, they might be bending current lines a little bit. So actually, we've already tested it out by removing probes 8 and 9. The electrovortex flow results I show at the end, we've removed probes 8 and 9, replaced them with brass fittings, which I hope is non-magnetic enough. But we have a Gauss meter in the lab that we can test it out. Upcoming.
Thank you. We still have time for questions, but questions in the chat. Any more questions from the audience, maybe? It seems that no, there are no more questions, so we just would like to thank you very much, Jonathan, for the very nice presentations and very exciting results Yeah. So yeah, thank you very much for your time, your presentation, and to share with us your experimental results. Yeah, Caroline said the same. Thank you for this nice talk. So thank you, Douglas, by the way, for to stay here today with us and to let Jonathan present these results.
A great pleasure.
Excellent, guys. So yeah, thanks everyone for being here today. Hopefully we will see you on the next talk next month in May. I will let you know in advance the title of the presentation and the speakers. Who will be Michael Nims from HCDR. Norbert, would you like to say something?
Yeah, thanks a lot to you for the organization and to John for the presentation today.
Excellent. So hopefully we will see you next seminar. Let's be in touch in the meantime. Take care, everyone.
Goodbye. Take care.
Goodbye.
Bye-bye.
Bye-bye.
So.